number of bright white LEDs that was so the tracking system could identify them. And when we take an image, basically what we do is we look for these bright spots, these either LEDs or reflective surfaces, and then we can identify it. And if we have multiple camera angles from multiple cameras, usually we can compute the position of the dot in 3D space. The problem is a single dot only gives us a single 3D position, which is nice if you just want to know where something is. The problem is a dot does not give us a rotation. And usually when we talk about tracking controllers or doing head tracking, of course, we need position, we need a rotation, we need to know where it is, and we need to know how it is rotated. That's quite important. So how do we get rotation? Well, rotation we can only get if we have multiple points in space. So what we usually do is that we have this target, and this target, as you can, for example, see on the right, which is an ART target for glasses to do head tracking. It has multiple spheres attached to these little sticks. So if we look at the camera image we get, we have an image which has multiple bright spots. Usually each of these little reflective spheres is a bright spot in the image. And the arrangement of these spheres on the target, so where they are, how long these little sticks are, and at what angle these little sticks are setting, that must be known to the tracking system. So the cameras give an image with just a few bright spots, and the tracking system knows, okay, there is this target that has exactly this configuration of spheres on it. And given this information and various camera angles, we can then identify the target, and we can identify how this target is rotated in 3D space. So with a target that has multiple spheres in a certain unique arrangement, we can then do positional tracking, which gives us the position for each sphere and therefore the position for the entire target. And we can do rotational tracking, giving us a full 6 degrees of freedom. And that is exactly what we want. And the same thing is also applicable for full body tracking. So, for example, if you know these mocap suits, if you have ever seen some YouTube video or something where mocap, so tracking of full human body or maybe just upper body with hands and arms is done, the actors usually have these weird bodysuits with bright glowing points or spheres on them. That is also so that they can have full body tracking. The tracking system can see all the spheres as dots. It knows that there is a skeleton. So usually when you do animation, you have a skeleton and then apply it to a 3D model because the bones and the joints are fixed of the skeleton. And therefore you can compute how the skeleton is oriented, how each limb is oriented, and then apply it to the whole body. And this these suits with the bright spheres on them allows you to compute the skeletal pose, that's the pose of the actor, and apply it to any mesh you want to. So you can have an actor play something out and apply it to a mesh, and then you get an animated 3D model. Quite funny, for example, if you look at the Jurassic World movies, there are some making offs of them, and they actually had, sorry, they actually had humans with full body mocap suits for the raptors that were running around and basically acting the raptors. And then the system in the background was doing the tracking and applying a transformation so that they basically gave the whole how the raptors acted and how their heads moved around. That was just actors being applied to the raptor model. Okay, so we have a camera-based system and we get a 6 degree of freedom tracking from it. The question now is, how well does this actually work? Like, is this a good tracking system? Is this a bad tracking system? And is this usable? You have to remember that depending on the use case, latency and precision is more or less important. For example, a mocap system for a movie should be really precise and capture small movements, but latency is not that important because what you do is you just capture the tracking data, but then you apply it afterwards. So you don't have anything real time usually, or just a small real time preview. So if there's a bit of a latency on it, it doesn't really matter. On the other hand, if you look at VR applications, we said that for VR, anything like above 50, 60 milliseconds is considered bad. So you want a really low latency. Well, basically with camera-based systems, they can be very, very good, but it depends highly on the cameras that you use. So you need a certain amount of cameras. It works with 2, but you want 3 or 4 at least, so that you get various different angles. That is important just in case you have some occlusion. So for example, if someone has the glasses on with the target on the glasses, and that person happens to have long hair, then the hair can occlude the view from the camera so that the cameras cannot see all the points or all the spheres, or some cameras cannot see spheres at all. So you want as many cameras as possible to get a good view and many angles and always see as much of the spheres as possible. The other thing that is really important is the quality of the cameras. And when we talk about the quality of the cameras, we have 2 major factors. One is the resolution, and the other thing is the frame rate. Resolution does not need to be extremely high to give a very good tracking system. For a camera that tracks up to maybe 5 to 10 meters, even something like 720p is already enough to give you a good tracking with high precision up to 1 millimeter. But what you want is cameras with a lot of frames per second. So if you have a camera that just does 30 frames per second, then you only get tracking data 30 times per second, and that is really not much. For example, the cameras that we use for our cave, which is the R6 cameras, they go up to 180 images per second in normal resolution. If you turn down the resolution, they can go up to 500 frames per second. So you see that, yeah, you can get really good cameras that give you tracking information very, very often. But of course, the better the cameras and the better the tracking system, this can get quite expensive quite fast. And as we said, in home setups, what you usually use is sensor fusion. So you can use cameras that are like only 60 FPS because you get data from the LMUs in between the camera frames. So if you don't have a few hundred frames per second, it doesn't matter. So these optical setups, they can provide very precise tracking and provide very low latency. You just need the high-end equipment to get there. And if you have just reflective spheres that you track and have the cameras do the flashing, that also has the advantage that whatever you have on the human body does not need to be an active component. So you don't need to worry about batteries or LEDs or cables or stuff like that. You can attach them to pretty much anything, which is a big advantage in some setups. And the other thing about these camera-based systems is that depending on the resolution and the quality of the camera and the amount of cameras you have, you can actually track a very large space. So especially if you go into the mocap movie sector, you sometimes have these huge rooms where actors can run around and move around. And there are many, many cameras along the walls. And with a high quality camera and enough cameras, you can capture everything and have complete freedom of movement in there. So it's a very flexible system that allows for a great amount of freedom. And as I said, this was also used, for example, in the original Oculus Rift that came out in 2016. And back then it was called the Oculus Constellation Tracking. And the image on the right is actually that is actually what the Oculus Rift looked if you captured infrared as well. So this had a cloth on the outside, and below the cloth there are these infrared LEDs, and there's quite a bit of them. And well, the cameras, the Rift came with 2 cameras. They could then see these LEDs and identify the position of the headset with it. And what you can see here as well is that the original Oculus Rift was not necessarily designed to be a room scale system that allowed you to move around in a larger area. Because if you look at the head strap, you can see that there are no LEDs on there. The LEDs were mainly on the head-mounted display itself, so on the device in front of your face, because it was originally designed to work more like in a sitting setting. It came with an Xbox controller originally. And when they later added the Oculus touch controllers, they sold them separately, and the touch controllers had a third camera with them, because that allowed to put one camera sort of behind you and then do room scale with that, so that they had all angles and could see you from any side. Another camera-based system is here we still have the example of the original PlayStation VR. PlayStation VR is, well, it uses camera tracking for the headset as well as the controllers. It uses visible light, however. So the headset had these blue lights on it, and the controllers had one pink and one red, like single light ball on top. And you had this camera system, these two webcams basically, that you placed above the TV. There was just like positional tracking for the controllers, because this is only a single colored dot, if you want to call it that, in the camera image. The headset, of course, had rotational tracking as well. The problem with the original PlayStation VR system was always that, due to it using visible light, meant that it worked best when the ambient light around you was not very bright. So best in dim environments, if there was a lot of sunlight or a lot of artificial light. If you were in a very brightly lit room, the tracking of the PlayStation VR 1 system was not that great, due to the decision to use visible light for it. Another camera-based system that a lot of people know is the Wii mode. So the Wii mode also uses a camera-based system, but it is the other way around compared to the PlayStation VR system. Because with the Wii, what you did, you got this Wii mode itself, which was this controller that was a slightly bit bulky. And you also got a so-called sensor bar that you placed under your TV. Thing is, the name sensor bar is like slightly confusing, because it does not do any sensing. What it actually does is, the sensor bar contains a couple of infrared LEDs, and the camera is actually in the remote. So the remote does the tracking, and it can then see the LEDs in the sensor bar and orient itself by that. So it knows, okay, this sensor bar is under my TV, so the TV is there. And it also had IMUs in it, so that the IMUs can do the actual tracking, and it uses the sensor bar to orient itself. Quite a nice system, and was very commonly used also in sort of hobbyists and developers, because it allowed quite a wide variety of applications and freedom to play around with, not just the original Wii games. Another camera-based system that works slightly different is depth cameras. So there were a number of different manufacturers that are offering depth cameras. And a depth camera usually gives you a depth value for each pixel. So in a normal webcam or RGB camera, you get an image that is just a two-dimensional array with a number of color values. And in a depth camera, you have same a two-dimensional array. They often have RGB cameras in there as well. So they quite often give you a color value as just like a normal webcam. But usually each single pixel also has a depth value that tells you how far this pixel is away, and therefore you get a depth image as well as a color image from a depth camera. And you can imagine that knowing the depth, sort of getting a 3D view for an image, can be quite useful and allow for a variety of applications that sort of do tracking and identify certain structures with the depth image. How is this depth collected? Well, there is there are various different ways, from stereo cameras, time-of-flight sensors, LiDARs, and so on. One example for such a depth camera would be the Microsoft Kinect. I don't know if you actually remember the original Kinect. I think this was maybe 12 years ago, something like that. So the original Kinect was an add-on to the Xbox, and Microsoft sold it as a gaming device, more or less. So what it was a special camera that you mounted on top of your TV, and you connected it to the Xbox system. And the Kinect had a VGA camera, so not great resolution, quite low resolution. It also had a microphone, and it had a depth sensor. And this depth sensor worked by projecting a grid of infrared points. And for each point, the system could then measure the depth. That also meant that the depth image was actually not the same resolution as the camera image. It was actually a lower resolution, but they intended it for a cheap gaming device. So I guess they considered it good enough for that application. The Kinect was then used to sort of recognize movements and gestures, and it even tried doing full body tracking for input. Like there was this mech game, I remember, where you could like do certain gestures to pull at levers and whatever there was. Yeah, the problem with the Kinect was that it never really worked that great. It was never widely accepted. There weren't not that many games for it. The games that came out for it weren't that brilliant mostly. And yeah, tracking was rough. So quite often the criticism for games that use the Kinect tracking was that the tracking is not reliable and not super accurate. And you can imagine that for a game, if stuff fails to recognize your gestures and what you do and what you try to grab, that is very, very frustrating. And well, it never really caught on. They also then later released the Kinect for Windows, and then they actually did another set quite recently, which is less focused on gaming, but more of generic depth cameras for development and industry. So the Kinect is still somewhat around. The original Kinect for the Xbox, not that great a success for what it was meant to be. However, it was picked up quite a lot by various programmers and developers who did a lot of cool projects with like body tracking, skeletal tracking that you could find on GitHub. So it was widely accepted as a decent device, just not for what it was meant to be. Another way the stereo cameras work is camera-based systems. The depth cameras work is camera-based system which uses two cameras. Intel, for example, had a range of these. This is an image you see on the right. The RealSense brand is discontinued now. Intel stopped developing these, but it is the principle is available from a number of other manufacturers like ZED. And stereo cameras, they don't have any type of special depth sensor. Instead, they create the depth image by using two RGB cameras. So they basically work like our eyes. You have two cameras, you know the distance between these two cameras, and you get two RGB images, two color images. And by having both these images and knowing where they are in relation to each other, you can then match these two images and compute corresponding points, and therefore compute a depth value for each pixel by the two from the two camera images. This actually works quite well, and it is quite common today in computer vision to use these stereo cameras. They have gotten a lot cheaper, and they are relatively easily available and readily available, and are often used when we need a depth image. And there is no dedicated time of flight or LiDAR or something wanted because these are simpler. Okay, now if we talk about navigation and depth images, we should also talk about an approach that is commonly used, and that is SLAM. What is SLAM? SLAM stands for simultaneous localization and mapping. SLAM is something that started out in life mostly in home applications for stuff like vacuum robots, navigation, these devices. So if you have one of these vacuum robots that drives around your house and that not only drives around erratically, but actually builds a map of your rooms, then this usually uses SLAM. It means that it uses some sort of sensor that can either be a stereo camera or a laser sensor or something. If it has a little like tower on top, it's usually a rotating laser sensor. And so it builds a map of its surroundings and then identifies where it is within this map. So it does localization, so it finds itself, and it does mapping. It actually creates a map of your surroundings. And you can usually see this. Usually they come with an app or something where you then get a map of your apartment or whatever it is where you live. And then you can see where it is. Some of the apps allow you to drive around like it's a toy or something. So it's quite common these days, and the medium to high range vacuums use these. Also self-driving cars, basically the same approach, have a map of your surroundings and identify where you are in it. Difference is that, the application self-driving car is slightly more critical than the application robot vacuum because, let's say, the effect of bumping into things is not the same for these two. Yeah. So why do we talk about SLAM and why do we talk about robot vacuums in the lecture virtual reality? Well, quite simply, this is an approach that is also somewhat used in VR systems. So SLAM basically can use any sensor. As I said, a robot vacuum may have a stereo camera, it may have a laser depth sensor, something like this. The idea is also applied in VR systems. So VR systems usually do camera-based tracking. And we already talked about inside out and outside in tracking. Well, inside out tracking is basically the same as SLAM-based tracking systems. So you have these cameras that are mounted on the head-mounted display, and these cameras observe their surroundings. And then they try to build a map of their surroundings. As soon as you move your head, they see more than what their field of view covers. They can sort of see all around you as you turn your head around. And so they try to build sort of a map of the room or whatever it is where you are. And then they try to localize the head-mounted display within the room. So you get a positional value and a rotational value. So you can do 6 degrees of freedom tracking with this idea. And this inside-out based tracking using cameras is actually quite common these days. So you have the Windows Mixed Reality headsets, the Quests do it now, Pico does it now. The Vive trackers are now available with inside-out tracking. The Vario Aero, I think, does it. There is just quite a large number of systems that use inside-out tracking based on this SLAM idea. Why? Well, because what you need is just a few cameras on the headset. And that means that it's quite easy to build. It's quite cheap. You don't need to set up anything outside the head-mounted displays. You can just put it on, calibrate the floor once, and you're basically done. So it's easy to use, it's cheap. And well, from a precision standpoint, it's actually quite good these days. So the first Windows Mixed Reality headsets, they had very low resolution black and white cameras. They were usually criticized for having not very good tracking. With the modern headsets like you get in the Quest 3 or the Pico Neo, they are still not considered the best in class tracking, but the tracking is quite good and easily enough, I would argue, for what you try to do in a home set. So talking about using cameras in head-mounted displays, how many cameras do I actually need? Well, two is enough, basically. The early Windows Mixed Reality devices, like you see on the top, this is a Dell forgot what it is called, Dell Windows Mixed Reality something, that just used 2 cameras on the front. Of course, more cameras are better. For example, on the bottom, the Meta headset that uses 4 cameras, which just gives you a wider field of view overall. And that means there is more to see of your surroundings, more feature point to detect, and therefore the tracking can be more stable, has a better chance of working well. So more cameras are better. So far, we have been talking about headset tracking. So that gives us the position of the head. The question is now, how does this SLAM inside out thingy actually work with controllers? And well, let's just say that the amount of cameras you have in the headset also influences how well the controller tracking works. What you do with the controllers is that usually the controllers do not have cameras in them. So they actually use a different type of setup. Instead, controllers usually are tracked outside in. So they use the cameras on the headset to track the controllers. Quite often, the controllers are equipped with either LEDs, or usually they are equipped with LEDs. And the cameras in the headset can then pick up the LEDs on the controllers and therefore track them. And well, as I mentioned earlier, this can either be done with visible light or with something like infrared light. So the visible light was used by the Windows Mixed Reality, for example. Some of the Vive inside-out devices also used the visible light. You get this weird pattern on the controllers, and you can usually see that the controllers have like a plastic ring on them. Quest 3 doesn't, but the others have mostly. And with Oculus, you don't see any LEDs because they use infrared, and that's just not visible to the human eye. So if we have lights on the controllers and the cameras in the head-mounted displays do the tracking, then the question is, what happens if the cameras in the head-mounted display cannot see the controller? What happens if I move the controller above my head or behind my back? Or what if there are only 2 cameras on the head-mounted display and it will leave their field of view? Well, we use the same approach in the controllers that we do in the head-mounted display, and that is sensor fusion. So we not only have the optical tracking system for the controllers, but we also have IMUs in the controllers that give us positional and rotational data. And what that means is that as long as the cameras see the controllers, we do the same thing as with the headset. We track with the IMUs. They are usually connected to the headset wirelessly via Bluetooth or some kind of RF connection, and they send their IMU data. And we use the optical data from the tracking system to control the drift and correct the drift. And what happens when the controllers leave the field of view from the cameras is that the IMUs still continue to work. So you get full IMU tracking as soon as the controllers are not visible by the cameras, and as soon as the controllers return to the field of view from the cameras in the headset, the optical tracking kicks in again. Now, that means that once we cannot see the controllers from the head-mounted display, we are reduced to just use the IMU tracking. And that means that, of course, we are affected by drifting. But the idea is that if you have controllers, well, they usually are sort of in front of you. They are sometimes below you where you might lose tracking from the cameras. Sometimes you have your hands maybe up in the air where you lose tracking. Well, you might even put one behind your back or something like that. But let's face it, usually you are doing something in front of you. And that means that most of the time, you actually have optical tracking from the headset. And yeah, if you just use it for like just the pure IMU tracking for a few seconds, if you lose sight of them for a few seconds, that doesn't really have a big impact. That's not that big of an issue. And if you do something behind your back or so for, I don't know, 30 seconds, a minute or something, well, then you can't see it anyway, and you can't be precise anyway. So Usually this is quite a good system, and in like most applications, this is not an issue. However, still tracking inside out for controllers as well as headset, as I said, is not considered the most precise system. There are more precise systems out there. So the big advantage of these systems is that they are very, very easy to use. So you just have to put on the head-mounted display. You don't have to do any external tracking setup. You don't have to mount any cameras in your room and do a camera calibration. It's just really put on the headset and go. And that's why they are used for many, many modern head-mounted displays that are currently available, especially the slightly cheaper variety, because the tracking is quite good. It is not considered ideal, but it is quite good. And it usually works in quite dark environments. If it is completely black, then the camera tracking, of course, can fail, but with the modern system, they don't need that much light, I would argue. There were a few head-mounted displays like the Vive Cosmos, I think it was, that was considered quite bad inside-out tracking because it needed a lot of light. So all the reviews said if you are in a dim room, not very brightly lit, then this just doesn't work properly. But modern systems are usually quite good in that regard. And the other disadvantage, as I said, is that the controller tracking is limited by the cameras on the head-mounted display, but as well, most modern head-mounted displays have 4 cameras arranged on them, so they have quite a good field of view and have quite good coverage. At times where you just had 2 front-facing cameras, they are gone for the most part, thank God. Okay, so we have talked about inside-out tracking and that most modern head-mounted displays use these. There is one other tracking system that is still very common that has been around since 2016 when the original HTC Vive released, and that is what is called SteamVR tracking. SteamVR tracking, well, it's called SteamVR tracking because it is developed by Valve and is what SteamVR mainly uses. The code name for the SteamVR tracking is Lighthouse tracking. So that's what it was called when it was developed by Valve and HTC in 2015. And it uses a different approach to tracking, and we will have a look at that now. So to understand how the Lighthouse tracking works, let's have a quick look at what a lighthouse actually is and what it does, because that's quite a good description at how this system actually works. So what is a lighthouse? A lighthouse is something that was used in navigation to give ships a fixed point and provide them with a landmark so that they knew where they are and they could find their way and avoid dangers. The lighthouse is basically a tower of sorts, and on top of it, there is a light that is sometimes rotating, and that light is very visible from a long range, so from far away when it's dark. So during day, it's usually not that important because you have light anyways, but at night when you can't see anything, the lighthouse provides you a landmark that is just visible from a very long ways away. And the reason why lighthouses work is because they have one attribute that is very important. They don't move. They are in a fixed position and you can rely on them being where they were yesterday. If the lighthouse moves, then you have quite a different problem. So how is this useful for tracking? Well, the idea of the Lighthouse or SteamVR tracking system is that you place a number of lighthouses at fixed positions. So you sort of give a number of reference points, and the device that does the tracking can then see these reference points, and if it has been calibrated accordingly, so when you move them around, you need to recalibrate the system, but if it has been calibrated once, and the device sees these lighthouses, then it knows where it is with relation to the lighthouses. And yeah, these lighthouses give off light, just like a real lighthouse. And the device that does the tracking, it can then detect the light, and it can use this light to compute position and rotation. So SteamVR headsets usually come with base stations, and these base stations are the lighthouses. So the image on the right are two of these lighthouse base stations. This is version 1, actually. It is the original one that was released in 2016. There has been an update ever since. The new ones look slightly different. The basic principle is the same. So SteamVR Tracking 1 was limited to 2 base stations and had a room scale area of up to 5 by 5 meters. These 2 base stations need to be synchronized, and back then they either used optical systems, so they needed to see each other, or there was a cable provided that you could plug in, which looked like a 3.5 millimeter stereo audio jack on both sides. So you had this long cable between them, or they were close enough that they could see each other. And the maximum number of base stations you could use was 2. The newer system, the SteamVR 2 system, actually uses Bluetooth and wireless synchronization. So that means that they are more variable in terms of setup, and you can also use more than 2 base stations at once. So not just 2 are able to synchronize, but a larger number is able to synchronize. And that allows you to add additional base stations for either more, better tracking, more coverage, or if your room layout was not just a big rectangle or something, that also allows you to better cover like arbitrarily shaped areas. And within these base stations, you have LEDs and you have lasers. And both of these use infrared, so you cannot see the light emitted from them. And what it does, it has the LEDs for flashing, and the lasers are actually coupled with rotating mirrors so they can sweep the room. So what we have here is an image of a base station without the outer cover. And if you look at like on the previous slide, this like glossy area in front, that is actually, that does not block infrared light. So infrared light goes through there. It's just visible light that is blocked. So that is why it looks black. And if you remove the cover, you get what you see on the right. So these 2 round things are actually the lasers with the spinning mirrors. So there are motors, or like, they are actually, I think, motors from HDDs that are in there, and the points on the blue surface, that are those are the flashing LEDs. So a base station is actually an active device, so it needs power, but it's just a stationary beacon, and it is giving off light. That is all that it does. It does not do any tracking by itself. So you need to power it, but you do not connect it in any way to a PC for tracking. It has a connection via Bluetooth, the new ones, so they can do firmware update, but it does not provide any tracking data. It's just a stationary beacon, so it's quite a stupid device in some sense. And what happens is that the flashing LEDs, they are used to synchronize. So the flashes tell the head-mounted display that a new cycle starts. And the 2 lasers are used to sweep the room, one horizontally and one vertically. So it's always flash, which means, okay, next cycle is starting, then one laser sweep, then the second laser sweep. And if you have multiple base stations, you can imagine that they need to synchronize. So without synchronization, just a number of base stations randomly flashing around and lasering around the room, that would just end up in confusion. So you need these 2 synchronized so that one flashes, one sweeps, second flashes, second sweeps, and so on, so that you get a coordinated system that allows the headset to do proper tracking. And as I mentioned, this synchronization can be done with cable, optical, or Bluetooth, depending on what version of SteamVR you have. And SteamVR Tracking 1 max 2 base stations and a max base of 5x5 meter. SteamVR tracking 2 is more than 2 and arbitrarily shaped areas. Okay, so what we have now is 2 or more base stations, and they are nice and in sync, and they flash and they sweep. And what do we do with it now? Well, the device that actually does the tracking is the headset. The headset is covered in a number of sensors, and the controllers actually do the tracking themselves as well with the SteamVR tracking. So these sensors that are spread over the headset, they can actually detect infrared light. And that's all they do. They are photodiodes. So they basically give a signal whenever they are hit by an infrared light source that is strong enough. And what that means is that these landmarks compare a couple to the sensors on the headset can do a very precise tracking with the base stations just being stupid emitters of light, and the headset actually containing all that is needed for doing the tracking. So the headset is connected to a PC and is giving the tracking data via USB. The base stations, they just have power. So these, you can see on the right an image of an HTC Vive Pro. And every single depression on the headset, the controllers also have these depressions. That's where a photodiode is sitting. So each of those depressions is a point where the headset can detect light hitting it. And they are set up in a way that usually they are just detecting light from the lighthouse base station. So they're looking for the right frequency and a certain amount of light hitting them. And then they actually give off a signal and say, yes, I've just been hit. So as I said, the LED flash, that is synchronization. So the flash can basically be seen by all of the photodiodes, and that means to the headset, yes, I'm getting a new cycle. I need to watch out for the lasers and see which point of me is hit when. And the laser sweep, that comes in from one side and goes through the room. It's a sweep. And so some of these photodiodes are hit first and others are hit later. And since we know, okay, we are in a new cycle, we can detect which photodiode is hit when. Same goes for the controllers. That timing, so that now is the beginning of the new cycle. It took so long to hit somewhere. That allows us to compute a position of the tracked device. And since we have vertical and horizontal sweeps, and a number of photodiodes on the headset, that allows us to compute full tracking information. So it's actually a timing-based system with the optical base stations. Okay, so SteamVR sounds quite complicated. You need a bit of a setup around, you need calibration. If you move the base stations, you need to calibrate again, you need to power the base stations. Ideally, the base stations should sit quite high, so I think it's recommended above 2 meters. Yeah, it's a bit of a setup, isn't it? It's just, you need to get quite a bit of stuff going and power it. And ideally, you want them screwed to the wall, because if you have them on mounts or something, they can easily move and that throws off tracking, and then you have to recalibrate. You see that it is quite a bit more setup process than for the inside-out tracking. So it's not as convenient, that's clear. And you have to have a lot of sensors on the head-mounted display and the controllers for it to work properly. The big advantage is that SteamVR tracking, it does work without external light sources. So it does work in complete dark, since the base stations are giving off light themselves. But you still have to be wary of very brightly lit areas, especially if there is a lot of sunlight. That can cause potential issues, that can cause interference. For example, if you have a room with a large glass side or something with very large windows, and it is a very bright day and the sun is blasting in, then SteamVR tracking can start having issues. Still, it's a very stable, very good system. And one of the biggest advantages of the SteamVR tracking system is that it is extremely precise. So it is considered one of the most, if not the most accurate system that you can buy on the consumer market. And given the cost of some of the other tracking systems that are out there, it is quite cheap. The Vive Pro complete set with the SteamVR tracking is 1,500 euros, with the headset alone being 800 euros. I think a base station costs between 1 and 200 euros. Or yeah, it's not super cheap, but it's still consumer market grade, I would say. Okay, so much for the basic tracking systems. Are there any questions so far? Okay, so I don't think there are any questions. Okay, so let's move on. As I said earlier, the second part of today, we will talk about output devices. So mostly head-mounted displays, but there are a few other types as well. So the question with output devices is, what can be used to display images or audio or other stuff? First of all, what does an output device do? We said earlier that mixed reality is not limited to just visuals, but that mixed reality can actually cater to all human senses. Of course, not all human senses are practical to deliver information to. So we only have hardware for visuals or opticals. We have hardware for audio. Stuff like olfactory, gustatory displays get a lot harder. So in this section, we will focus mainly on displaying stereoscopic images, which is often done with head-mounted displays, caves, devices like these. But, well, if you look at what you have readily available and what you can buy for mixed reality, usually you are limited to visuals that is done using head-mounted displays that can be done using projectors or now TVs, LED displays, stuff like that. You can do audio. So audio you usually do by headphones or speakers, or you can do haptics, so feel and touch. I would argue that that is very limited, however. Controllers sometimes have vibration in them to do some sort of haptics. There are various like ultrasonic devices that try to give you some touch feeling, but overall this is very, very limited. Some gloves try to do something like force feedback, but usually you are limited to controller vibration if you don't have any like research or development devices that are usually not commonly and readily available. So we will stick to visuals for now, and we should first talk about how can we actually classify these devices. Well, there are two ways to display images and two types of devices to display images. One is a single display device and the other is a multi-display device. So what are these two? In a single display device, you have one screen that is showing the entire image. And in a head-mounted display, you may also use two images to show the entire image. Is still basically it's the same approach. You have a display that shows the entire image. A multi-display means that a single image is spanning over multiple displays. So you can see why a head-mounted display would be a single display, even if it uses like two small screen inside, because there is one image and the image is shown on an entire screen. While multi-display means that you span an image over multiple displays. So for those of you who were at the LRZ or who know the cave at the LRZ, it means, for example, there is one continuous image in the entire cave, but it is multiple displays that are displaying it. So this might be a screen, it might be projector, something like that is commonly used when you build a multi-display installation. And HMDs, we have had it in the past. It gets confused quite often. That's why I'm having it here again. A head-mounted display may have two screens in it. It's still a single display device. So let's give you an example of a multi-display system and how it works. We said that a single image is spanned over multiple output devices. And these output devices, they may be screens, they may be projectors, whatever is used to display an image. And the image is not necessarily just one 2D thing. So it's not necessarily a single plane. In a cave, for example, you have the displays at an angle. It still displays a single image covering all the output devices. It's just important that one continuous image is displayed over these devices. And you also don't necessarily have borderless output devices. So especially in the past, low-cost video walls were built using standard TVs. Of course, TVs have a bezel. In the past, the bezel was a lot thicker than it is with modern TVs. And so you had basically a gap or a border between the individual images, and still they displayed one continuous image or tried to display one continuous image, and that made them a multi-display device. And how do you get this image, or where do you get this image from? Well, multi-display may be driven by multiple sources. So you may have multiple playback devices or multiple computers that are putting out the image. You can have one source that pulls to multiple output devices, or you can have multiple sources. Both makes it multi-display. And the image on the right, for example, gives you an example. You would have 4 projectors, each projector projecting onto a quarter of the entire screen, but they are showing one continuous image. So that's a classical setup for a multi-display device. Okay, so let's have a look at some multi-display installations. So where is this approach actually used? So first of all, why? Why would we add complexity and do multiple devices, having to synchronize them? Why do we go through all this trouble of building multi-display installations? Well, despite their shortcomings, multi-display installations do have some advantages that can make them very viable. First of all, resolution. Single image devices are usually limited in resolution to what the technology can do. So a single screen, if you buy like a TV or something, then you get 4K, maybe 8K. If you have a projector, that usually has a fixed resolution, and if you want a bigger image, you can put it further away, put a different optic in it that scales up the image, but it doesn't change the resolution. With multi-display devices, you can actually build higher resolution screens or protection surfaces or something than a single device would allow you. So image quality and resolution is one big advantage of multi-display devices. The other advantage is that you can better cover the field of vision of a user, and you can surround a user with the image that you display. So again, those of you who know the cave, they have seen that you can actually be surrounded by screens and stand in a room that will actually put you within the virtual environment. So that would not be possible with a single display device. You would have to build a screen that has 90-degree angles. So again, with the size, it's just not possible. At this point, you need a multi-display device for that. So quite specialized use cases, quite high-end use cases usually. But if you go there, there are some things where you need multi-display installations and multi-display devices, and a single display device just can't keep up. First of all, power walls. What is a power wall? A power wall is usually a term that means a single large-scale display that is usually just a flat surface. So it's a very large-scale display. Powerwall does not necessarily need to be a stereo device, so it can be used to be a mono device as well. So sort of think of it as a multi-display cinema, same thing. There is no fixed definition what a Powerwall is and what functionality it has to support to be a Powerwall. It is a bit of a marketing term as well, but you hear it quite often when you read about or hear about large-scale visualization screens. A Powerwall also does not necessarily need to be multi-display. If you have a very high-res projector, you may also build it as a single display device. But if you want to go really, really high-end and pump up the resolution, then you usually go multi-display with them. The example for a Powerwall, you have seen it here at the LRZ. So our Powerwall has a screen of 6 meters by 3 meters and 15 centimeters. And well, our Powerwall is a bit of a hybrid between a single and a multi-display installation. Why? We use two 4K Sony Cinema projectors to project onto the screen. But these two projectors, there are two because each projector does the image for one eye. So one projector does the image for the left eye and the other projector does the image for the right eye. And there are polarization filters in front of the two projectors so that with the polarization glasses that you wear, you can then separate the stereogram and see 3D. So, okay, now you might be thinking, well, that sounds like a single display, right? Yes and no. So the reason why we say it's a multi-display is because these 4 projectors actually get 4 input sources. So due to their age and the HDMI standard of when they were built not being able to transmit 4K at 60 FPS, we actually have 4 cluster nodes that provide the image via 4 inputs, and the projectors then make one continuous big image from it. So it is fed as 4 discrete images, and then the image is composed by projectors. And of course, having 4 workstations or graphic servers to compute the images means that each graphics card needs to compute a lower resolution, which gives you a better overall performance as well, which is quite useful when you are used to dealing with very large scale data. So this is what the Powerwall looks like. We have two Sony SRX T420 projectors. They have 21,000 lumen, and each is doing 60 frames per second. So that gives you 60 frames per second per eye, or 120 frames per second in total. And we have stereoscopy with polarization filters. The Powerwall also has a tracking system because it is designed to display interactive content, and you want to be able to control it via an input device. And we are using an ART system. It's a 2nd-gen ART system for the Powerwall. That means it's an optical tracking with 6 cameras, which gives you around 1 millimeter precision, and it gives a tracking frequency of 60 hertz, so 60 data frames per second. And these 6 cameras are mounted on top of the Powerwall. And as I said, it has 4 input channels to connect to the for servers in the basement. So a Powerwall is basically a large-scale flat screen. If you don't have a flat screen, the alternative is to build it curved, and that would be a curved screen. Who would have guessed? You maybe know curved screens from at home. Some may have a high-end gaming monitor. They tend to be curved these days. Well, the big curved screen multi-display thingy is more or less the same, just a lot bigger and wouldn't usually fit on your desk anymore. A curved screen that we are talking about here is basically a Powerwall, just that it's not flat. It has a curve to it. The advantage of the curved screen, of this curved Powerwall, is that a user can stand in front of it, and due to the curvature of the screen, the field of vision is covered much better. So a curved screen tends to give better immersion than a flat Powerwall. Of course, this depends on how far you stand away, on how the curve is, and so on. But usually it is better coverage of the field of view and therefore better immersion. Again, it may be monoscopic, it may be stereoscopic, it may be single display, it may be multi-display. That is quite the same as with the Powerwall. Curved screens usually tend more to be multi-display due to the fact that with the curve, you have to distort the image. And that is a bit easier if you have multiple devices that you can aim at multiple parts of the screen. So you get a better overall picture. Of course, that usually means that you have to also take the curvature into account when you render the image and distort it accordingly. Okay, so moving on from screens, and then let's go to the cave. Again, we have already talked about the cave during our history of VR section. So hopefully you all remember this and remember who invented it, because she was quite an important person for us. So the cave, to repeat that, was originally presented in 1992 by a Carolina Cruz Nera. It's a room you can walk into, and the walls of this room are displays, and the idea is that you surround the user with the virtual environment. And as a slight fun fact, actually, Carolina Cruz Nera was at the LRZ in, I think, 2017, because she wanted to see what we have here and what her idea has become over the decades. So caves may be six-sided. It is possible to build a six-sided cave, but they don't have to be. A six-sided cave is quite difficult, requires you to usually have a wall that is able to open and close like a door, so you can walk in and close it. You may also have like a 5.5-sided cave. That is possible as well, so that there is just a smaller opening, but many times caves have 3 to 5 sides. Especially a 5-sided cave is usually considered enough, because you can walk in and you are oriented towards the back wall, so you don't see what's behind you anyways, and you don't see the real world, and you are, for your field of vision, completely inside the virtual environment. That's why usually the sixth side is considered to be possible, but not worth the effort. So the basic idea is that the cave allows you to enter the virtual world, to walk into it, sort of like a simplified version of Star Trek's holodeck. Coming to the cave at the LRZ, we have actually renewed our system this year. So ours is brand new, and you can see an explosion diagram on the right showing you how the new cave is set up. So we have this substructure, this subframe on the outside. That is these poles that are floating slightly away from the actual surfaces. And mounted onto this subframe is are the LED cabinets. So a cabinet is a housing for LED displays, and within a cabinet you have a power supply, you have a hub board which just connects everything, and onto the cabinet to the front you clip the LED panels, which are the actual screens and completely borderless. And basically what you do is you mount a number of cabinets next to each other, you clip the panels in, and that allows you to get a continuous screen without any bezels or borders in between. And you set up any shape and size you want. And the resolution is then determined by how far two of your pixels are apart. So you buy these LEDs with a so-called pixel pitch. Our cave, for example, has a pixel pitch of 1.25 millimeters. That means that the center of two neighboring pixels are 1.25 millimeters apart. And combined with a screen size of 3 by 3 meters, like 3 by 3 meters and 3 centimeters, something like that, gives us a resolution of 2400 by 2430 pixels per wall times 5 walls. So in total, we have 1620 LED panels. And the cave does active stereo. So with LEDs, you do not have polarization filters. It's not possible. You have to fall back to active stereo. And we are displaying at 120 hertz. So it's always 8 milliseconds for the image of the left eye, then 8 milliseconds for the image on the right eye. And we have the shutter classes that we talked about last time. These are connected via radio frequency, so wirelessly, and that gives you a 3D image. The cave also has an ART tracking system, but since it's brand new, it's a lot newer than the one we have in the Powerwall. The Powerwall was a 2nd-gen system. The new cave has a 6th-gen system. It's again an ART optical tracking system. It has around the same precision as the Powerwall system, maybe a bit better, but like in this range, it doesn't really matter anymore. The big advantage of the new cave is that the cameras can record up to 500 frames per second. So the tracking is done a lot faster than with the Powerwall system that we have had for a decade now. Okay, and with that, let's move on to head-mounted displays. What is a head-mounted display? Well, if we look at the name, it's a display that you mount on your head. So on the right side, that's technically correct, but not quite. Usually a head-mounted display has a number, or all head-mounted displays have a number of components that they all share. So what is inside a head-mounted display? Well, you have a housing, and in this housing, you usually have 1 or 2 screens, and these screens are used to show the actual images, the actual stereogram. It may be 1 or 2 screens, that depends on the setup, but if it's 1 screen, then 1/2 of the screen shows the image for the left eye, the other half of the screen shows the image for the right eye. And if it's 2 separate screens, then, well, yeah, again, 1 screen left eye, 1 screen right eye. The principle is the same depending on 1 or 2, doesn't matter. And the 2 images are displayed side by side, so next to each other. And in front of each eye, you have a lens. That is very important. We will talk a little bit later about why you need a lens, but, well, that's basically the principle behind a head-mounted display. And apart from the tracking system, like that's what they all have inside them. Type of lens may vary, the screen setup may vary, but you need that to display stereoscopic content. So let's talk a bit about the screens first. There are various screen technologies and effects that they can cause that are used in modern head-mounted displays. First of all, let's think a bit about what we actually want from a screen that we put in a head-mounted display. We want very low latency. So for those of you who remember LCD screens of yesteryear, so from the 90s, the notebooks, they were really slow, and moving the mouse, you could see a trail from the mouse. And even now, and especially like 6 to 8 years back, you had this big discussion where it was like, do I get an IPS screen, which is nice color reproduction, but it has a 5 millisecond response time, which means that it's not great for fast gaming, stuff like that. Well, for VR, of course, we want a screen that has a very, very low latency. So good response time and fast image updating. The second thing is we want high brightness. You might think that, well, why do we need good brightness? This is like stuck to my head and there's a face cascade all around and it's dark anyway and light from the outside is blocked. Yes, it is, but still you have lenses and stuff that usually takes a bit of the brightness away. So you do want a display with good brightness. The next thing is we want our headset to be high immersion and good quality and put us in a virtual world that is as close to possible as the real world. So we want good and ideally correct color reproduction. So if you get a screen that has really washed out colors or grayish blacks, that's of course not very nice. We want vibrant colors. We want nice dark blacks. We want no backlight bleeding or any of that nonsense. We just want a good color reproduction overall. And of course, we want resolution, very, very high resolution, especially for VR head-mounted displays. Resolution is one of the key factors. Why is resolution so important? Well, we have lenses, and lenses plus screens means we might have what is called the screen door effect. What is the screen door effect? Screen door effect is if you put your face very close to a screen and maybe have a lens that works as like a magnifying glass, you can see that the screen is not one continuous image. It is actually made up from pixels. And even worse, each pixel is made up from subpixels. So if you look at a screen that isn't extremely high resolution through a lens, you might see this effect that makes it look like you are looking at the image through a screen door being these like mosquito net door thingies that some people have in their windows. And you don't want that. You don't want it to look like there is a grid in front of your image. So screen door effect, as a rule of thumb, is usually connected to resolution. A low resolution display means that there is more screen door effect, while a higher resolution display usually means that there is less screen door effect. However, there is a bit more to it than this. Why? Because it also depends a bit on the display technology that you actually use in your head-mounted display. So you may have heard that some head-mounted displays use OLED, some use LCD. There is now mini LED, so there is a variety of display technologies that you could use. And well, the big discussion is usually between LCD and OLED, and some of the newer head-mounted displays also use mini LED. For example, the MetaQuest Pro is a mini LED headset. So comparing LCD and OLED, LCD is quite cheap and it has good sharpness, but it tends to have washed out blacks, which isn't very nice. OLED, on the other hand, it has vivid colors, so it has a very good color reproduction, very saturated colors. It has very, very nice blacks, so black surfaces usually really look black. On the other hand, it is expensive, and especially older OLED screens can suffer from what is called burn-in. That means that if the image doesn't move for a longer time, there can be sort of a remnant of that image constantly burned in. That, for example, is an issue with some phone screens that use OLED, where you have the bar on top that is always the same that might burn in. So yeah, if you look at that, OLED also has high refresh rate. It sounds like, well, it might be the better choice. Should be like, okay, it's more expensive, but it gives me the better display, right? Well, not necessarily. So sometimes manufacturers tend to cheat a bit. So LCD might not necessarily be worse than OLED. And the reason for this is that a single pixel, as I said earlier, is actually not just a single pixel, it's made up from subpixels. Usually subpixels means red, green, and blue. And depending on what color you display, these subpixels go brighter or less bright. And especially with OLED screens that are quite expensive, manufacturers tend to or have a tendency to sometimes cheat a bit. So what they do is that they play around with the subpixel layout. In LCD screens, usually you have one red, one green, and one blue subpixel for each pixel. So each pixel is the same. With OLED, you can have what is called the pentile layout, which means that a subpixel is not exclusive to a pixel. So you can have subpixels or a subpixel of one color shared between pixels. And that doesn't really matter on a phone, for example, because you're far enough away to not see it because it's so small. But if you add being really close to the screen, like you have in a head-mounted display, and having lenses, like you have in a head-mounted display, then you may suddenly see that. So in the image on the right, you can see that the pentile and RGB layout, the RGB, everything is the same. While the pentile, it's a repetitive pattern, but you can't clearly identify one subpixel or which subpixels belong to one pixel. And that's because some of those are shared. And on the right, you see that looking at this icon, the left half of the icon zoomed in looks a bit more coarse because it's pentile layout, and the right hand side of the icon looks a bit better because it's actually an RGB subpixel layout. So if you buy an HMD, actually check what screen it has and listen to the reviews. Be wary that there might be a quality difference. Okay, so we now have chosen a screen for a head-mounted display. What else do we want our head-mounted display to be? Ideally, we want it to have a very large field of view, so to cover most or as much as possible of our vision. And we want it to be very low weight. So the question with both these attributes is, where do we have to place the screen? And for both of these, screen placement needs to be very close to the eyes. Why? First of all, having the screen closer gives us better field of view. You can just try this out if you put your hand in front of your head at like an arm's length, then your hand only covers a small amount of your field of view. It's just a little thing in front and you can still see your surrounding for the most part. However, if you put it just right in front of your eyes, then it will cover most of your field of view. And it's the very same with the screen. If you put it really close, then it will cover most of your field of view. If you put it far away, you have like a tiny screen in the middle of your field of view. So for a head-mounted display, having it closer is better in terms of field of view. The other advantage of having the screen close is that screens and the whole casing that comes with it and everything actually has weight. So ideally, you want everything as compact and as close to your eyes as possible so that you have less leverage and that the weight from the screen has less effect and is causing less force on your head. This is especially important if you move around your head, turn it fast. You want everything to be as compact and as tight and as close as possible so that inertia isn't dragging your head around. Okay, so we'll just build a head-mounted display with a screen very close to the eyes. Everything's fine, right? Let's just up the resolution so we can see nicely and we're good, right? And no, there's an issue with that. Again, try holding your hand very, very close to your eyes. Can you actually see your hand clearly or is it all blurred? Yes, it's blurred. So same goes for a screen. If you take a screen and you put it very close to your eyes, yeah, you'll see like a 100-year-old. You won't see anything sharp, which isn't very good if you want to do immersive VR. And that's why we need lenses. That is the reason why all head-mounted displays have lenses. So what the lenses actually do is that they compensate for the small distance between the display and our eyes. And well, it's the same as glasses, basically. So these lenses, they bend the light that is coming from the displays, and that allows us to have a screen that is very close to us and still see a sharp and clear image. And the other effect of these lenses is that they can actually bend the light a bit and simulate a wider field of view. So it allows us to put the display close to our eyes, see the image sharply and nicely, and still have a very good field of view. But again, keep in mind that this is also something that is built into the head-mounted display. So again, lenses should be small, they should be light, they should not add a lot of weight to the whole system. So choosing the right lens is also an important factor when building a head-mounted display. Many times you see what is called a Fresnel lens. So if you just build a big classical lens that is just this round shape that we know from lenses, that means that the lenses are actually quite thick. And if you build them from glass, they can get quite heavy, and we don't want that. We don't want thick lenses because that means that the headset gets bigger. We don't want heavy lenses. That means that it's more comfortable and more to carry on your head. So no. What Fresnel lenses do is that they can reduce weight and thickness quite a lot. And that is by approximating the curvature of the lens in like little pieces. So you can see on the right how a Fresnel lens is designed. You take the lens that you actually want, and then you take out like the solid bits in the middle and just leave the curvature on top. And you get this like lens. If you look at the Fresnel lens, it looks like it has like lots of little rings and there's like little grooves all around. That gives you a lens that is a lot smaller, that is a lot lighter, and usually has like in terms of refraction, very similar effect to a normal lens. So that is very good. The problem is that since it's not a continuous curvature, but these little approximated bits, it has the possibility of adding glare and of adding God rays to the image. So God rays, these rays of light that you can see, or glare effects that can be due to light hitting the sides where it's not supposed to. Fresnel lenses were the go-to lenses in VR for quite some time. So the earliest headsets in 2016 didn't have them. Then they switched to Fresnel lenses very early on. And that has been the standard for a few years. But we are now seeing its successor. So we are now seeing a new generation of lenses, and those are known as pancake lenses. So for example, the MetaQuest 3, the Pico Neo 4, the MetaQuest Pro, these have pancake lenses. And pancake lens is basically a colloquial term for a lens that is just very flat. And these are usually designed that rely on half mirrors, so mirrors that only let light through from one side in combination with polarization filters. And what that does is that it's not just one lens and light passes through it once, but due to these mirrors and filters, light can bounce around in there, it bounces back and forth, and therefore have the same effect as a normal lens and still achieve a very, very flat design. And usually you can identify HMDs that have pancake lenses by their size. They look a lot smaller and like a lot shorter in front of your eyes. So With the lenses being flatter, that also means that the display can be closer to the eyes, and the whole head-mounted display can be built smaller. The problem with the pancake lenses is that they tend to have what is called less optical efficiency, which means less light goes through, basically. So you need a slightly brighter display to compensate for this, which is not that big of an issue in PC VR devices, so in devices that are tethered to a PC and have an external power source. But of course, with standalone devices, not the greatest thing, but still not that big of an issue. And usually the effects of the pancake lens, the advantages, compensate for the disadvantages. So we've now chosen the lens. We need to talk about the effects of the lens on the image, because if you look at an image through a lens, usually you have distortion. And distortion means that we need to consider it when we render our image. So if we just render an image and display it onto the screen and then look at it through a lens, we get a distorted image. And we don't want that because that's bad. We don't want it to wobble around and look weird. So what we need to do is we need to consider which head-mounted display we are rendering our image for. And we need to know which type of lenses it uses and which distortion this is applied by these lenses. And we then can apply an inverse distortion to the image we render. And then if we look at it through the lens, it's the correct image again. Easy. And I'm not going into much detail how this is done because the distortion is usually different depending on what head-mounted display you use. And usually this is done by the SDK or whatever you're using to render for the head-mounted display. So the manufacturer is providing the distortion for you usually. You don't need to implement that manually in any way, shape, or form. Okay, so we have had a VR boom since 2016, has like stalled a bit, but is still going strong. So there is quite a large number of devices that have flooded the market in the last 6-7 years. So we will now have a look at some head-mounted displays that are currently available. Please keep in mind that this is not in any shape a complete list. There may be more. I'm just trying to give you an overview of what there is so you have a good idea and can make an educated decision if you want to buy something or want to do something. But again, not an exhaustive complete list. But before we talk about the devices themselves, we want to talk about two concepts that have become quite popular over the last few years and that are quite common with some standalone devices nowadays. The first one is pass-through. What is pass-through? This is something that came up originally with like the Quest 1 started it a lot, the Quest 2 improved it, and is now a hype with the Quest 3. And what it means is that the headset actually has cameras. And these cameras, while they are usually used for inside-out tracking, may also be used to give you an image of the outside world in your VR headset. So it's basically AR in a VR headset. So you have one or more cameras mounted on the head-mounted displays. For tracking, it's usually 2 or more. And if you have one camera, you just display this camera image. If you have 2 or more camera, you usually stitch together an image of what is in the real world in front of your head-mounted display. And then you display this image inside your headset. Usually you have 2 or more cameras anyways, because you want good field of view for tracking. And 2 or more cameras can then give you quite a decent field of view of what is around you. And some head-mounted displays also combine this color image with depth sensors. This might be a LiDAR system or a time-of-flight system. For example, the Vario devices use LiDAR. The Quest 3 has a time-of-flight sensor. And what they do is they not only create a color image surrounding you, they also create a 3D map of your surroundings so that you can do things like having AR and having objects in front of your sofa or behind your sofa, and it actually, your sofa covers the devices, stuff like that. So quite a big topic at the moment. The pass-through of the Quest 3, for example, is quite good. As I said, the Vario headsets use LiDAR, which is very good. So quite an exciting topic that is quite common in the media these days. The other thing is what, well, the slide says link. The idea is to have a standalone or headset that can be tethered to a PC, either using a wired connection with USB or having a wireless connection with Wi-Fi. So standalone devices are devices that have their computational power and everything they need built into them, kind of like phones. And they then work like gaming consoles. So you can just download content onto them and play them without a PC or being connected to anything. However, with Pico, with Meta devices, you can also tether them to a PC so that they work like a PC VR headset. And this is usually done using high-speed USB ports. I think they now use USB 3.1, used to be 3.0 with the Quest 1. And the USB link usually transmits the image data. However, often this is compressed. It uses some sort of codec, and they also tend to lower the FPS. So it's not necessarily running at what the display in your headset can give you due to limitations of the USB. This may vary depending on what device you are using. So be aware that if you use if you use link, the image quality and the latency may go down compared to standalone use. And via Wi-Fi, this is also possible. It's called AirLink with Meta, and Steam has now released for Steam VR actually Steam Link, which can connect directly to your standalone device without using AirLink. That is usually done using the newer Wi-Fi standards if you go wireless. So Wi-Fi 6E and upcoming Wi-Fi 7 has very good bandwidth. However, be aware that this is not something that you might want to do via long distance. So it's not like you can set up a router like 2 rooms over and connect to your HMD. Usually you need to be quite close to the access point or router. So you get actually the pretty much full transmission speed of the Wi-Fi you have. Okay, and with that, let's move on to some devices. We will go through them by manufacturer. This is not a rating or anything. So this is basically an arbitrarily chosen list of manufacturers and what devices they are currently offering, they have had in the past. So don't take it as a rating or something like that. First, HTC. HTC was very early on in the VR game. They came out with the original Vive alongside the original Oculus Rift in 2016, and they were a major player in the VR game. So the Vive, many considered it a better VR device. It was sort of a bit of a, well, yeah, I don't think there was a clear winner, but many people preferred the Vive because of the Steam VR tracking that was just a lot more precise. And it seemed to be the more professional device. They have since released the Vive Pro as a successor to the Vive, which was designed more for the industry. It had a better head strap, it was more durable, it had built-in audio, better resolution, of course. They then released the Vive Pro Eye, which was basically the same device, just with added eye tracking, and have since released the Vive Pro 2, which does not have eye tracking, but just an upgraded screen, upgraded visuals, and is still working with SteamVR tracking. So SteamVR tracking 2 since the Vive Pro. The Pro 2 is a very solid device. It's not something amazing anymore, but it's a good device. And the big advantage of the Vive series is that they have had the same controllers since day one. So if you developed something for the old Vive, the controller mapping, the controller models, that all stayed the same and is still just as valid as in day one. They then went into the standalone market with the Vive Focus and the Vive Cosmos. Yeah, those were not that really impactful, I would argue. They then released the Vive Flow, which is a bit of a weird thing. It's a headset that only has 3DoF tracking that tethers to your phone to watch stuff on. So it's a bit weird. It was one of the first devices to use pancake lenses. It's very lightweight. It's very compact, but it needs a phone either connected via wired connection or wirelessly to provide content. So it didn't get good reviews because no one really knew what to make of it and what to use it for. So a bit of a weird one, this. The Vive, as I said, was originally released in 2016. 2 years later, the Pro arrived, and then a year later, the Pro I, and the Vive Pro 2 is still available to this day. It is their latest release. It has a resolution of 2,448 pixels by 2,448 pixels per eye. Its displays can display up to 120 hertz. And it has a 120-degree FOV, and the Vive Pro, Pro I, and Pro 2 actually use the SteamVR tracking version 2. So that allows for more than 2 base stations, larger tracking area. And it feels bulky nowadays. The Pro 2 looks pretty much exactly like the Pro did, and the Pro looked very similar to the original Vive. So it is a device with the aesthetics of VR in 2016, same for the controllers. It is considered a bit bulky and a bit outdated these days, but it is a solid device. Can't argue with that. The Focus and Cosmos series, they started those in 2019 and have updated them since. Yeah, well, these are standalone headsets. As I said, they never were actually that impactful. They were not really cheap, and the Focus 3 is the latest one in the Focus series. It's a standalone headset. It uses inside-out tracking. It has quite good resolution per eye and screens, but it just never really caught on. It could never hold up to the Meta devices. The Quest was considered cheaper and having a better app store, so it just didn't really get sold all that much. The Cosmos, originally released in 2019. In 2020, they released the Cosmos Play XR and Elite. It's also an inside-out tracking device. It also has decent resolution per eye. They went away from SteamVR with this one, have their own Vive reality ecosystem. The Cosmos was originally criticized for having not very good tracking and needing a lot of light to work properly. So again, it was not really that cheap, and other devices were just considered the better deal. So yeah, it's still around, but it never really was that impactful in the market. The Flow, as I already said, is a device that has a very small form factor. It was designed to look a bit like a pair of sunglasses. Well, it is a bit thicker than that, but they went towards that aesthetic with it. It has flat pancake lenses, but it only has 3DoF tracking. So it's sort of a device that you use to sit down, lean back, and enjoy some content, whatever that content may be. It needs an external battery. It needs an external smartphone to deliver content to it. And as you can imagine, a smartphone is not the most powerful content provider for a VR headset. So content is also a bit limited. Overall, it just never really got very good reviews. When it came out, there was a bit of media coverage about and around it, but haven't heard much of it since. Liz, do you know what happened to it? It just completely
Like, was at some conferences as like more of a technical here, look
Yeah.
how cool this is, but it was never really adopted by a larger market.
I think even we had some project partners who said like, oh yeah, this might be useful, but then nobody ever went for it because it's so limited. Yeah, so Flow, yeah, weird thing. They actually have another device, which is their latest one, which is the Vive XR Elite. That has actually a similar form factor to the Flow. Its design is slightly different. It has a battery. It also has the flat lenses from the Flow. This is a 6-stop device, which is a lot more useful. The resolution is a bit lower, but it is standalone. It has controllers that are coming with it. And it has a hot swappable battery, which is quite an interesting feature. So you can sort of pull the battery pack that is at the back of the head strap off and replace it with the device still running, which might be a useful thing if you have a use case where you want to use it continuously. You can have multiple battery packs and swap them out and keep going. Overall, again, the XR Elite, it's not that cheap, and there are better devices out there. It's just, it has a basic feature set and it's not a bad device, but for the price, you tend to get something better. Overall, Vive, HTC, the whole series, it has gone down. So it started out really strong with the Vive. It was there early on, but ever since they have dropped off, and it feels like their latest devices have not really been met with that much interest. So yeah, bit sad, but well, that's the way it goes. Okay, so that's it for HTC and their lineup. Then let's move on to the big one, Oculus or Meta. So Oculus started out, we talked about it with their Kickstarter, and were later on bought out by Facebook for a lot of money. And early on, they built the Rift series. So there was the original Rift, and then later on the Rift S, which was dropped immediately. I think it lived for less than a year or something like that. It was dropped stupid fast. The original Oculus Rift was a solid device, though, was quite nice. They then went to the Oculus Go, which was a cheap 3DoF device, and then they came out with the Quest. And the Quest is very, very popular up to date. Quest 1, Quest 2, and Quest 3. The Oculus Rift is gone. The Oculus Rift S was gone really fast. It was a bit of a weird device as well. Had inside-out tracking, sort of resembled a Windows mixed reality thingy with controllers. Was not a bad device, but was not amazing either. And the Oculus Go was also popular for quite a bit, especially for stuff like 360 content, 360 video content, but was then killed off eventually in favor of the Quest series. So speaking of the Quest, the first Quest was, like all Quests, a standalone head-mounted display, and it was marketed to be a cheap VR device that does not need a PC. And if you think about it, that's quite a big advantage, because a PC to drive VR content is not cheap. So you need quite a powerful PC, good graphics cards. Having a standalone device without any cables or anything, not being attached to anything, is quite a nice thing to have. So marketing this and designing this as a sort of VR games console with their own meta store was quite appealing to a lot of people. So the battery, the CPU, the GPU, everything is inside the headset. It uses inside-out tracking with 4 cameras. You can actually see the 4 cameras in the picture on the right, 2 at the bottom, 2 at the top on the sides. And this is not the Windows Mixed Reality tracking. This is their own development. And the original Quest had a resolution of 1440 pixels by 1600 pixels, but it only had 72 hertz screens. So that's not that amazing. It was a bit low. Still, overall, the original Quest is a decent device, especially if you connect it via USB to a PC. Quite a good device. We still use them for various applications. The controllers are nice. Tracking is good. It works quite well. So after the Quest 1, Meta, it still says Oculus here. I just can't get used to not calling it Oculus, sorry. After some times, they then released the Quest 2. And the Quest 2 was, well, it was the successor, and I guess you could say it was better, but it was also, it was designed to be a bit cheaper, it feels like. So the Quest 2 had improved screens, it had improved GPU and CPU. The whole thing basically is a smartphone inside. So an upgrade there, an upgrade in terms of processing power. It was cheaper than the Quest 1. And it was cheaper for a reason in some regards. So first of all, the head strap of the Quest 2 is considered not as good as the setup for the Quest 1. And Oculus or Meta sold an Elite head strap as an expensive accessory to it. Think about that what you want, but yeah, the head strap that comes with it is not that great. It's okay if there is just one person using it. If there are multiple people using it and you have to adjust between sizes for different heads, then the Elite strap is a lot better. Yeah. It also had a shorter battery life. And most of all, the Quest 1 had a IPD adjustment like you want from a head-mounted display. The Quest 2 also had an IPD adjustment, but only stepped. So it had 3 settings, and you have to choose the one that is closest to what your IPD is. Yeah, yeah. It's not that great. So stepless is better, and it was a big criticism for the Quest 2, but overall it was very cheap. You can now, it's still being sold. The Quest 3 is actually not a successor. That meant it was discontinued. It is still being produced and is still being sold. And in a sale, I think you can get it as low as 300 euro for a cheaper version. So it is quite a cheap way to get into VR now. And ever since this year, like in the beginning of November, Meta has released the Quest 3, which now Oculus is wrong. It's called the Meta Quest 3. I still can't use it, sorry. Again, the Quest 3 has an updated SoC, so it has more processing power. It's about twice as fast, according to the specs, than the Quest 2. Again, it has improved display and improved controllers. You can see the controllers at the bottom. There is one big difference. They lost their ring. So these are now similar to what the Meta Quest Pro uses. They do not have this big ring around them anymore, which makes them a lot more compact. It also has 2 front-facing RGB cameras, plus a time-of-flight depth sensor in the middle. That is quite important for the pass-through mode. The pass-through of the Quest 3 is actually quite good. Can't argue with them there. They did a good job. It's a full color pass-through. There is a bit of distortion exactly in the middle where the images are stitched together. But overall, as I said, it is very good. And the depth sensor means that it can map your room. So something like choosing the safe space where you can move around can be done automatically, where it just says, okay, please look around, and it will find the biggest flat area and give you that as this is your play space now. It can detect obstacles, and it has hand tracking, like everything, the Quest 1 added hand tracking, Quest 2 had hand tracking from the beginning, Quest 3 now has hand tracking as very good input method. You can do stuff like you can view like Windows YouTube videos in front of you, and you can grab it with your fingers and walk out of the room with it and take it outside on the balcony and watch it there, stuff like that. So that's really a lot of added value to this device. It also has pancake lenses, which means it's a lot more compact than the Quest 2, and yeah, color pass through and hand tracking is a lot improved compared to the last models. And then they have one other device in their current lineup, after the Quest 3, and that is the Quest Pro, which is actually older than the Quest 3. So that was released about a year ago. Quest 3 was released this year. So the Quest Pro is considered to be the high-end successor to the Quest. It is also a standalone headset. It has 90 hertz screens, and it also has color pass-through and improved controllers. It also has eye and face tracking, which the Quest 3 does not have. Now, since we are talking about Meta devices, a quick word about accounts. In the beginning, when Facebook bought Oculus, you could continue using your devices with Oculus account. They then added the Facebook account. So you needed to link your Meta device to a Facebook account, which was a big problem for some people. And it actually meant that the Quest 2 was not allowed to be sold in Germany for several years due to data privacy issues with this Facebook account thing. Meta has since moved away from that, and they have created a separate Meta account, which is supposedly separate from a Facebook account. It's Meta, you never know. So you don't need a Facebook account anymore. You need a Meta account to use these devices. So that has changed a few times in the last few years. And as far as I'm aware, the Quest 2 is now available for purchase again in Germany ever since they moved to the Meta account. Okay, so much for their current lineup. Then let's move on to Valve. Initially, when the headsets came out in 2016, Valve was joined up with HTC to develop the Vive, but they have since made their own headset, which is actually quite a few years old now. I think it came out in 2018 or 19, I'm not sure. Liz, do you remember?
It was long ago.
It was long ago. It was very long ago. Yeah, so the Valve Index, the resolution is not the greatest anymore. It's decent, but not the greatest anymore by today's standards, but it has very fast displays up to 144 hertz. And this just tells me it was in June 2019, so 5 years ago. Thank you. Yeah, the special thing about the Index is less the headset, which is a decent headset with SteamVR tracking. The interesting thing is the controllers. The Valve Index has special controllers that have these grips. And what you do is you grip the controllers and then you pull tight this strap. And that allows you to grab and release the controllers, and the strip holds it to your hands. And there are sensors in the grip that track your finger positions. So you can actually grab and release objects in VR using these controllers. So that allows for some interesting applications. The Index is not a bad device, even by today's standards. It's just that times have moved on and Valve has not released a new product so far. Okay, that's the only HMD Valve released. The world is waiting for another one, but well, it's Valve and they work with Valve time, so who knows if it will ever happen. Windows Mixed Realities, this is something that is a bit of a thing of the past, but I think I still want to cover it. So initially, Microsoft designed the mixed reality headset. It was sort of a reference design that was then implemented by various manufacturers. Microsoft delivered the software stack for this. And well, whether you bought an Acer, an HP, a Lenovo, a Dell, or something else, Windows Mixed Reality headset, you basically got the same device. They were not that great. They were very cheap. But they had a small FOV and overall they felt cheap, and the initial Windows Mixed Reality tracking was not brilliant. So there was a reason why they were cheaper. The controllers were also reference designed by Microsoft. They were a bit bulky and weird, and the tracking was not great, and they weren't very economical. And yeah, not the greatest thing of the world, but a cheap way to get into VR. They all used inside-out tracking. And ever since, a few manufacturers have gone on to refine the design and build their own Windows mixed reality headsets. So one of them was Samsung. They released the Samsung Odyssey and later on the Odyssey Plus. It's a headset, well, yeah, it had a decent resolution for the time when it came out. The inside-out tracking was a bit improved, but it still had only 2 cameras, which was not the greatest thing in the world. And you can see the controllers there. Those were actually the refined, more ergonomically designed controllers than the original Windows Mixed Reality controllers, as bulky as they are. The original ones were just like rectangular thingies that weren't very nice to use. So yeah, the Odyssey Plus was a big improvement over the original Windows Mixed Reality devices, but it was still never the big hit. HP actually did a bit of a better job. They released the Reverb and then, more importantly, the Reverb G2, which is actually not bad. The G2 was co-developed by HP, Valve, and Microsoft. It has a good resolution of 2160 by 2160 per eye, and it has an improved Windows Mixed Reality tracking system with 4 cameras. The interesting thing about the G2 was that they later on released an Omni Concept Edition, which is a fancy name for basically a G2 with some added sensors. So it was a special edition that featured not only eye tracking, but also a pupillometry sensor. So that measures your pupils. It had a face camera, or has a face camera, and a heart rate monitor. And well, the purpose of this device was for industry applications, research applications, where you want to do user studies and how users react to some content and measure stuff like how do their pupils dilate or contract, what is their heart rate doing, stuff like that. So for research, it was quite an interesting device. And it was even considered one of the top devices for home use for some time. But again, it is now a few years old and times have moved on. And with that, we'll move on to Vario. Vario is using a slightly different approach. Vario is designing VR devices for industry, basically. So they go ultra high end, but also in price. So they have the Aero, which is their cheapest one, which was recently lowered a lot. I think it was around 3,000 euros before and is now 1,000, which is a decent device. The Aero is a good device. The VR3 is, yeah, it's one of their older ones. The XR3 is still a very good device. I got to try it. It is brilliant image quality. It has a LiDAR depth sensor, so it's very, very good. I love the XR3, I have to admit. The interesting thing about the XR3 is that in order to optimize image quality, they designed the lenses in a way where the PPD, so the pixels per degree, so given a certain field of view, you have a field of view in degrees, and usually you have a screen and lenses, and that gives you have so many pixels per degree of field of view. Bio decided that like right in front of you, that's where you look. So that's where we need more pixels. And in the side areas, we don't look there. So we need less pixels there. So they went with a variable PPD, pixels per degree, to give you better overall image quality right in front of you. And it is really the image quality of the XR3 is very good. And the LiDAR depth image is also very precise and very good. So it is a really high-end device. The problem is that the Vario XR3, the focal edition, including the yearly subscription dev packages, you can, I think, get up to 15,000 euros. So yeah, it can get stupid expensive. And Actually, I think 2 weeks ago or something like that, they released the XR4, which is their latest and greatest headset. That has dual mini LED displays. You can see that the resolution is stupid high. It's 3840 by 3744 pixels per eye. That gives you 51 pixels per degree, which is pretty much the highest so far. Field of view at 120 degrees horizontal is always good, also very good. And it has 20 megapixel pass-through cameras. So that's really, really high. Again, it can cover full